Tell me about Graham's number.
Well, that's kind of a joke in a way. I mean, there was a combinatorial theorem whose proof used very kind of recursive multiple inductions. When that happens, you tend to get large numbers. And this was a problem, the following. You take an n-dimensional cube, already think about that, it has 2 to the n vertices. You join any 2 vertices with a line segment, so you have 2 to the n, choose 2 line segments. You color them red or blue, any way you like. The question is, can you always find 4 of the vertices so that all the 6 line segments are the same color, and these 4 points lie in a single plane? Normally, if you pick 4 points on a cube, 4 vertices, they'll span a 3-dimensional volume, but these are flat. Will it always happen, no matter how you color it? Said, yes, it will always happen if the dimension n is large enough. How large is large enough? Some really big number. Such a big number, you can't use ordinary notation. You need some arrow notation, just like the Ackermann function, much, much worse. And the best lower bound when this happens seems to be 13, seems to be the right number. But this big number, it's kind of in Wikipedia. In fact, it was in the Guinness Book, the largest number that ever really occurred in mathematics. And it's just very large, that's all. And it seems the true answer to the problem might be 13 or 14, which just illustrates the gap between what seems to be true and what we can prove to be true. It's a pretty big gap. You'd like to close it down a little bit. So it's not really mathematics significant. It's just something that people can kind of mention, think about. Graham's number, what is that? It's a big number. How big is it? Well, it's so big that how many digits does it have? Well, about the same number. It's so big. You say, really?